Last time, we're in the middle of proving the following theorem here. Collection of L lines, collection L of n lines in general position subdivides the plane into n squared plus n plus 2 over 2 regions. Right. What was general position again? A collection of lines is in general position when every pair of lines intersects, so no parallel lines, but yet no three lines intersect in the same point. So all lines intersect, but every intersection point is just a two-line point, not a three-line point or more. An important property about lines in general position. So if you have a bunch of lines in general position, you take away one line, it's still in general position, right? Because it's what defines general position is something that pertains to all lines. Every pair of lines intersects, so any pair of lines of a subset intersect, because the subset is in the set. And every three lines don't intersect like this, so for any subset, any three lines don't intersect like that. Because they're not existence properties, they are universal properties within the whole set. So they're inherited by subsets, those properties. And of course, like when you put lines in a two-dimensional plane, it creates regions. One line creates two regions, two lines, four regions. Three lines in general position give you 7 regions. If they intersected in the same point, you'd have 6 regions. And then the theorem is that n lines in general position always subdivides the plane into that many regions. All right. Proven by induction. May not seem like it, but it is an induction proof. So one line yields 2 regions. That's the base case, one line. One line yields 2 regions, and for n equal to 1, this polynomial here is 2. So they match. Good. Induction hypothesis. Again, with induction proofs, you must state the induction hypothesis clearly. For clarity's sake, you should state the target conclusion as well. Right? This is the hypothesis. This is the conclusion. You assume the hypothesis is true. Show the conclusion must be true as well. That's the direct proof approach. Once in a while, you might use contradiction or contrapositive, but usually not. All right. So we want to show that. So you assume n lines give you that many regions. And you want to show that n plus 1 lines give you this many regions. That's the statement. That's the predicate. N lines, this many regions. That's Pn. So n plus 1 lines gives you this many regions. That's Pn plus 1. Before going any further, let's simplify the expression. N plus 1 squared plus n plus 1 plus 2 over 2 is equal to n squared plus 3n plus 4 over 2. All right. Well, L will be a collection of n plus 1 lines in general position. Take one line, H, and remove it. So, L has n plus 1 lines. How many lines does L minus H have? How many lines does L minus H have?
N number of lines.
N lines. Since it has n lines, and what about those lines? Oops. Not has, but consists of. What about those lines? What's special about those lines? What's special about the lines of L?
They're in general position.
All right, so
Which would
L
be-
minus H consists of n lines, and what's special about those?
I assumed that was a question I was already answered when I said general position.
The intersect, yeah, more. The pairs intersect,
They're in general.
and triples don't intersect. They're in general position still, which are still in general position. So since we've got n lines in general position, what's got to happen?
Find the regions as the n squared plus n plus 2 over 2.
They make that many regions. Why?
That's the assumption.
What's the assumption called? Yes, what's that assumption called? The induction hypothesis. So the in induction proofs, the assumption
Yeah, the induction
hypothetical, yeah, the hypothetical assumption has a fancy name. It's called the induction hypothesis, and wonderful. Okay, wonderful. What's my class? Sacre el beb. Sacre el beb. The induction. It's called the induction hypothesis. So you have to say that. The induction hypothesis implies that L minus H defines n squared plus n plus 2 over 2 regions. Okay, now let's put H back into the arrangement. So there's H. Now, of the other n lines, so H is the n plus first line. Of lines 1 through n, what do they do with respect to H? Because of general.
They all cross it.
They all cross H. Each other line crosses H. Do they ever cross in the same point?
No.
No. Each of the lines 1 through n, each cross H once, and never in the same spot for any two of those lines. Right? So you've got, one of those lines, another one, another one, another one, another one, so on and so forth to the last one. So you have these many intersection points. So since H intersects the other n lines, H passes through this many of the n squared plus n plus 2 over 2 regions defined by through L minus H, right? So L minus H defines this many regions. How many regions of those n squared plus 2 over 2 does H pass through? Well, every time H intersects one of the lines, it passes from one region to another. So how many regions did it pass through? Right, this is line 1, line 2, line 3, line 4, blah, blah, blah.
It passes through n amount of regions.
Ooh. Anyone else want to try? Almost.
N plus 1.
N plus 1, right?
N plus 1.
Because, yeah, you get the, like, this would be region 1, region 2, region 3, region 4, blah, 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 region N plus 1. Right? N plus 1 of those regions. Right? Each region it passes through gets cut into 2. Cuts the region into 2 subregions. So L itself, well, this gives a total number of gain. This gives a total gain the blah, blah, I'm not saying it. So the increase in the number of regions when H is added in is therefore how much? The total increase in the number of regions. Each region that H passes through, so like this was a region, right? This was a region, and then that region got cut into 2 subregions. Subregion A, subregion B. So every time you cut a region in 2, the number of regions increases by what?
My arithmetic's pretty rusty, but I think it doubles.
That old song from the 80s. 1 step forward and take 2 steps back. Except this one is take 2 steps forward, then take 1 step back. Right? The region that you had got cut in 2. So the old region is gone and then replaced by 2, giving you an increase in total increase of no. The old region is gone, giving you a net increase in -1 regions. And then you put 2 regions in its place, giving you a total increase of...
If you're doing that for every region, then it doubles.
No. All the old regions are gone. All the old regions are gone. Let me show you. So here's 3 lines. Let's add in a 4th line. So how many regions we got here? 1, 2, 3, 4, 5, 6, 7. So now let's add in a 4th line if I can find a way to do it. So we had 7 regions before.
Oh, I thought you were just asking what the amount of regions it cut, the regions it cut, but not all the regions it didn't cut through. Not all the regions are gone.
1, 2. Right. No, the regions you cut in half. Right. So
cut in half.
You're just talking purely the number of regions. So here we're passing through 4 regions. So there were 7 regions to start. 1, 2, 3, 4, or no, sorry, 1, try it again. 1,
Yeah,
2,
you
3,
increase it by 4.
5, 6, 7. Anyone care to clarify what's going on?
You would increase it by 4.
Yeah,
Because
you
you're
increase it
doubling
by
the
4. Right. So the increase in the number of regions here is what? Right, so here, this is the fourth line.
It's equal to the number of lines that there is after you add H.
2A, 2B, 3A, 3B, 4A, 4B, 6A, 6B. How many regions did we increase? We went from 7 to what? How many regions we got now? We got 3 red ones and 8 blue ones.
You went to 11.
Right, so that's an increase from 7 to 11, which is how much? 4.
Which is equal to the number of lines, which is 4, which is double the amount of regions you've cut through.
We cut through n plus 1 regions. The number of regions increases by n plus 1.
Yeah, that's what I've been saying this whole time.
Is it? Right, but I mean, the quantity we're looking for is n plus 1. Right? Right? N plus 1. That's the fourth line, and we increase the number of regions by 4. The 4 regions we passed through were each cut in 2. So the number gained is 4, not 8, 4. Right?
Isn't that what I said 5 times now?
You keep saying double.
I said double, or the number. I said double the regions you pass through, or the number of lines plus 1.
It's the number of lines plus 1.
Yeah.
The number of lines. Right. The number of lines plus 1. But when you double the regions you pass through.
But I changed the number of lines plus 1
right,
instead of several
I
times.
apologize. Okay, I apologize. I misunderstood. Okay. So the total number of regions defined by L is what? So we started with this many, and we added this many. So it's n squared plus n plus 2 over 2 plus n plus 1, which is n squared plus n plus 2 plus 2n plus 2 over 2, which is n squared plus 3n plus 3n plus 4 over 2 as required. Right, that's what we were looking for. That quantity, this polynomial is right. Where'd it go? Right there. All right, we wanted that n plus 1 lines gave you this many regions, where this polynomial simplifies to that. N squared plus 3n plus 4 over 2. And here's how we got it. We started with this many. We increased the number by this many. And these add up to that. Okay? So in the homework for this section, chapter, we have number 3. So a collection of planes. So instead of lines, let's talk about planes. So we're going to put a plane in 3 dimensions. A plane in three-dimensional space. Again, it cuts three-dimensional space in half. So if you have a bunch of planes in three-dimensional space, a bunch of two-dimensional planes passing through three-dimensional space, then again, you're going to define regions, some number of regions. Okay? So a collection of planes in general position means the following. Every 2 planes intersect in a line. So planes are not parallel. Did everybody take Calc 3? Has anyone not taken Calc 3 yet? I think that probably most of you took it already. In it now, okay. All right. So, you would have thought about planes already, but, I mean, it's not much of a leap. You can, if you haven't thought about it, it's not hard to see. So, planes in general position, so this is for homework. Which number is this? Number 6. For chapter 6, of course. We have a collection of planes, P, in general position. Okay, so this means 1, every pair of planes intersect in a line. So planes in 3 dimensions, they can be parallel, of course, or if they're not parallel, then they must intersect. So here, these planes intersect in a line. 2, no 3 planes intersect in the same line. So, this doesn't happen. So I can't have another plane passing through this collection here. Alright, so this needs to become dashed. Good. Alright. So that doesn't happen. 3 planes have to intersect at a point. Any 3 planes intersect at a point. So that would look like this. Oh, let's see. So they intersect like here, though this is not the best possible picture here. That's not bad. So all 3 of these planes intersect, and this line is No, this line is fine. Ah, these need to be dashed now. Okay, something like that sort. Every 3 planes intersect in a point, and no 4 planes intersect in the same point. Okay, so I'm not going to attempt to draw that. So with a bunch of planes in general position, again, they define some number of regions in 3-dimensional space, and the number is actually right here. It's n to the third plus 5n plus 6 over 6. And we want to prove that. To prove it, well, the base case is, again, one plane. One plane gives you 2 regions. And then 1 plus 5 plus 6 is 12 over 6 is 2. So that's great. The base case is easy. And then the induction step is not too bad, because with the induction step, it's really quite the same as what we just did with lines. So we'll prove in that P defines n to the third plus 5n plus 6 over 6 regions in 3D space. So the way that works is as follows. For the induction step, you take n plus 1 planes. You take a collection P. It's got n plus 1 planes in it. Okay. Then you take one away, just like we did in this one. You take one plane away. The plane P intersects the other planes in one line each. And those lines on plane little p that come from the intersection with the other n planes, those lines have to be in general position on plane little p. So those n lines in general position on plane little p, they define this many regions on plane little p. But those are the number of regions right here that plane little p passes through. So the total gain in the number of regions from this on n planes is this. And that'll give you the number of regions on n plus 1 planes. So we want to write out a nice induction proof for that statement. And that will, it will mostly follow along with the way this one looked that we just did. The one about lines. Not much different than that. Okay? All right. Moving on. We're going to go to the second principle. So we've been doing the first principle of mathematical induction. And in the first principle of mathematical induction, the basic idea is the proof for step 99 follows from step 98. The proof for step 100 follows from the already proven step 99. The proof for step 101 follows from the already proven step 100. So on and so forth. You just prove the steps one at a time, and each step, n plus 1, follows from the step previous to it, step n. With the second principle of mathematical induction, the next step doesn't follow from the one before it. It follows from some other previous step. So formally, it looks like this. So the second principle of mathematical induction. Which is it's equivalent to the first principle, although it takes a little more wordiness to talk about it. Sometimes called strong induction, and it goes like this. To show that for all n, P of n is true over domain D equal to 1, 2, 3, 4, 5, so on and so forth, like that. So in order to show that this is true, you first prove 1. P of 1 is true. That's the base case. And then 2, the induction step is a little different this time. Here, the induction step is not that Pn implies Pn plus 1. The induction step is that P1 and P2 and Pn. So all the previous steps imply Pn plus 1. P1, P2, P3, P4, all the way up to Pn, that all of those imply Pn plus 1. Why does this work? Why does this work? Well, given that P1 is true, and P1 implies P2, right, we get that P2 is true. P1 is true, and then P1 implies P2. Well, since the hypothesis is true and the implication is true, the conclusion better be true. Now, instead of thinking about P2 and forgetting about P1, you bring P1 along with you. So given that P1 and P2 is true, are true. Given that P1 and P2 is true, and P1 and P2 implies P3, we now get that P3 is true. Hold on. Go upstairs again. Right. So given that P1 and P2 is true, and P1 and P2 implies P3, you now get that P3 is true. Given that P1 and P2 and P3 are true, well, is true, and P1 and P2 and P3 implies P4. So each time your induction step, the hypothesis grows a little bigger. So given that P1, 2, and 3 are all true, and P1, 2, 3 implies P4, we get P4 is true, etc., etc. So you just keep going like that as far as you need. The basic idea with the second principle of induction, like I was saying, is that step n plus 1, the proof for step n plus 1, doesn't necessarily follow from step n. It follows from rather, it follows from some step or steps within steps 1 through n. So not every time does the next step follow from the previous step. The next step follows from some combination of previous steps. The basic example of this, really the simplest example, and then the second principle is a little bit difficult to wrap your head around the first couple times you see it. But once you get used to it, it's really just the same thing. So the basic example is the following. So let's show that every integer n bigger than or equal to 2 can be written as a product of prime numbers. Okay, consider a prime number itself to be a product of primes. So, for example, right, so like 10 is equal to 2 times 5. 20 is equal to 2 times 2 times 5. 60 is 2 times 2 times 3 times 5. 105 is 3 times 5 times 7. 89 is just 89. It's just a prime by itself. 13 is just 13. Just a prime by itself. Consider it to be a product of primes just to make the statement easier to say. I mean, if you were to say every integer n bigger than or equal to 2 is either prime or a product of primes. Okay, fine. You know, you can, if you want to be sort of, you know, more, you know, precise about the language that way, that's fine. But let's just consider a prime by itself to be, you know, to be a, by default, a product of primes. Right, like, what else? 243, right? That's 3 times 3 times 3 times 3. So every number is a product of primes. N bigger than or equal to 2. 1 is not, because 1 isn't prime. So the proof is by the second principle. So the base case is n equal to 2. By the way, 2 is prime, right? 2 is a prime number? Yes? No?
Yes.
Yeah. What's the definition of a prime number?
Divisible by exactly two other numbers. Well, two other integers.
Yeah, just one in itself. A number p is prime when p and 1 are its only divisors, which 2 satisfies. It has the distinction of being the only even prime, right? But it is itself prime, right? Because there are no other integers between 1 and 2. Anyway, I mean, if you didn't consider 2 to be a prime, then this theorem wouldn't hold, right? Because, you got to have 2's in there. 60 and 32 and 64, so on and so forth. So 2 itself is a prime. And therefore, a product of primes. Period. Induction step. So writing the induction hypothesis requires like, a notion of quantification. Writing it sort of in a readable fashion. It's going to require require you to use quantification. So the induction hypothesis. So here we're starting at not at 1 but at 2. So let me write this down. So the base case wasn't 2, wasn't 1, it was n equal to 2. So we'll just fix that. P2, P3, P4, all the way up to Pn implies Pn plus 1. How can we write that in English? Assume this is true. This is what we need to assume. So assume that what? Right, and we're trying to show, right, and what's Pn in this case? Pn is the predicate, n is a product of primes. That's what Pn is in this case. So let me write it over here. Product of primes. So how do we say, right, so this is what? 2 is a product of primes, 3 is a product of primes, 4 is a product of primes, and 5 is a product of primes, and 6 is a product of primes, and n minus 1 is a product of primes, and n is a product of primes. How do we say that without repeating ourselves that much? So 2 is a product of primes, 3 is a product of primes, 4 is a product of primes, blah, 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 blah. N minus 2 is a product of primes, n minus 1 is a product of primes, and n is a product of primes. How do we say all that without repeating ourselves so much? Assume that every integer Okay, you there? Every integer from where to where is what?
Every integer from 2 to n is a product of primes.
Yeah. Every integer, and yeah, you could say every integer from 2 to n is a product of primes, or every integer in the set 2 to n is a product of primes. That's what Pn is. Pn is n is a product of primes. We're assuming that 2 is a product of primes, 3 is a product of primes, 4 is a product of primes, 5, 6 is a product of primes, 7 is a product of primes, n minus 4 is a product of primes, n minus 5, n minus 4, n minus 3, n minus 2, n minus 1, and n, that all those guys are products of primes. So we say it in a nice compact fashion like this, and it's going to require some kind of quantification. Assume that every integer in the set from 2 to n is a product of primes. Now, we need to show that what? Show that what is true. So we assume the hypothesis is true, and we want to show that the conclusion is true. And what is the conclusion in this case? Pn plus 1, which is what?
N plus 1 is a product of primes.
Exactly. Show that n plus 1 is also a product of primes. So there's two cases. If n plus 1 is prime, which it might be, right, like n plus 1 is 89 or something like that, then it is, by convention, a product of primes. If n plus 1 is not prime, then what happens? Come on, why did that happen? If n plus 1 is not prime, then n plus 1 equals what? What happens when a number is not prime, right? Like 105 is not prime. 105 is not prime. Why? The definition of prime is that, its only divisors are 1 and 105. But no, 105's got other divisors. Like what?
Like 5.
Like 5. Like 7 and 3 and 35 and 21. Right? So 105 is 23 times 7 times 5. Right, it's 21 times 5. So it's a product of two smaller numbers. Right? So if n plus 1 is not prime, then n plus 1 is a product of
Prime.
not yet.
Well, product of numbers.
Product of two smaller numbers. Sorry, is a times b, where a and b fall into what set?
Prime or not prime?
Yeah. But what set in particular on the page here that we're wondering about? This one? That one here? This one? Or no? Do they fall into that? If I said n plus 1 is a product of two smaller numbers, what is smaller than n plus 1? I mean,
n.
yeah, less than or equal to n. And bigger than or equal to 2, because they're not 1. N plus 1 is equal to a times b, where a and b are elements of the set 2 to n. What did we assume about elements in the set from 2 to n?
That they're a product of primes.
They're product of primes. So by the induction hypothesis, A is equal to P1 to Pn, where each, well, A is equal to this. A is equal to this, and B is equal to Q1 times Q2 up to Qm, or I shouldn't use N here, right? PS QT, where each Pi and Qj is prime. In other words, A and B are products of primes. So now, n plus 1 is equal to A times B is equal to P1 dot 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 to PS times Q1 dot 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 to QT, which is, well, all the P's and Q's are primes. So n plus 1 is now written as what? I've just written n plus 1 as the product of P1 to PS and Q1 to QT. That is a
Product of primes.
product of primes. That's it. So the fact that n plus 1 was a product of primes has nothing to do with the fact that n is a product of primes, right? Because n is not a divisor of n plus 1, no matter what, when n is at least 2. When n is 1, it is, but, not that case. Right, so for example, the fact that some big number, 2100, is a product of primes has nothing to do, well, follows not from the fact, follows not, Yoda, doesn't follow from the fact that 2099 is a product of primes. Rather, it follows from the facts that 70 and 30 are products of primes. So, for example, 2100 is equal to 70 times 30. Well, 70 is equal to 2 times 5 times 7. 30 is 2 times 3. 2 times 3 times 5. Right? Which is a product of primes. Right? 70 is a product of primes. 30 is a product of primes. 2100 is a product of 70 and 30, and so is a product of primes. Right? The fact that 2099 is a product of primes doesn't help you determine that 2100 is a product of primes. It's just that 2100 can be broken into smaller chunks. Okay, I've taken up enough of your time. So, all right, so next time I'll have another example. I think you're really going to like it. So we'll see you on Monday, okay? Have a good weekend.